Hi guys, welcome back. If you are back, that is because you have actually written down some things about inverses using the rule of 4. If you haven't, please pause the video and do it now. Okay, so if we think about the situation of inverses, the inverse undoes, and the way it does that is it does the inverse operation in the reverse order. In class, we talked about an example of, putting your foot in a shoe, or maybe first putting a sock on, then putting your foot in the shoe and then tying. And then if you wanted to undo that, you would have to untie your shoelace, take your foot out, take the sock out, off. And so we have this inverse operation happening in the reverse order. Now, if we consider an actual function and go through each one of these, maybe it'll help. So let's say we have the function f of x, we could also say y, is equal to, let's do negative 2x plus 4. Now, if I wanted to say this using math, I would say, take a number, multiply it by negative 2, and then add 4. If I wanted to do the inverse, f inverse of x, and that's how we write it with a little negative 1. It's not to the negative 1 power, it's an inverse. F inverse of x, we would take a number and we'd subtract 4. And then we'd divide by negative 2. Now, we can simplify this a little bit. We can call this negative 1/2 x plus 4. F inverse of x is negative 1/2 x plus 4. Now, if we think about this graphically, the graph reflects across the line y equals x. So here I have our line y equals x drawn in here, y equals x. And let's graph both the function and its inverse. I'm going to do it quietly. Why don't you do it as well? So here is the line, our function, f of x equals negative 2x plus 4. Now the inverse function is going to reflect across this line, so let's see. That should be a 2, shouldn't it? Silly me. All right, and as I graph those points, let's see how it does. Shoop. Ah, I see it now. It does appear to be reflected. Plus 2, just kind of cram it in there on the side. Okay, so we see it situationally, we see it visually. Now let's talk about the table of values. You may remember the domain and range are switched. Maybe you said x and y are switched. That works. So if we have the function and the inverse, so the function f of x equals negative 2x plus 4, x and f of x. When we plug in negative 2, negative 1, 0, 1, and 2, this is what we get. For the inverse function, negative 1/2 x plus 2, we get this pair, but switched, 8, negative 2. We'd get this pair 6, negative 1. And if we see 1, 2, 3, 4, 5, 6, 6, negative 1, there it is on our graph. We have 4, 0. We have 2, 1. And we have 0, 2. Aha. Proven. Now the equation, this is the one that is the most complex, and maybe it's because there is a lot here. There's a lot to learn. So before we left, we were talking about composition of functions. Remember FOG, f of g of x? Well, if we plug a function and its inverse, if we plug an inverse function into a function, if we compose inverse functions, our output is always x. Our output is what our input is. And that's all well and good, but there's something else I want to show you. Remember this idea about domain and range being switched? We can use this here too. Now remember, we've already figured out what the function and its inverse is. We've proved it visually, we've proved it using a table of values, but we can do it with an equation, and it works, I think, a little bit easier when you have multiple steps. So let's see. If I switch my x and my y equals negative 2x plus 4. Now, I can switch my domain and range, so let me try switching my x and y. X equals negative 2y plus 4. If I then solve for y, watch what happens. I end up subtracting 4. And then I divide by negative 2. And this might look familiar. We're doing the inverse operation in the reverse order. I get y equals negative 1/2 x plus 2. Voila. There you have it, folks. We will do a Desmos activity to bring some of this together and how logarithms and exponents relate using this information with the law of the rule of 4. Okay, love you guys. See you later.